Greetings and welcome to the recitation video for problem set number 4 of Chemistry 221. In this problem set, we're going to focus on chapter 4 and what the Lewis structure has to offer, which is a pretty cool chapter. Like the other recitation videos that you've seen before, try the problems on your own first. Make sure you show all of your work. Don't just give me the answers. A periodic table will definitely be helpful as you complete this problem set. mhchem.org/per-tab is the one I recommend that you use. You don't have to watch this video from start to finish. You can, by all means, scrub through it using the slider at the bottom of your video. You can also put me on 1.25 speed or 1.5 speed, whatever works for you, to go through it as you need to, which is great. And I definitely want you to self-correct all problems. The ones you get right should have some kind of self-correct symbol next to them. The ones that you miss, and again, it's no problem to miss, just correct them. All right, put the actual answer next to it. Make sure that I can see that you know what the actual answer is. Mark every problem. All right, you don't turn in any self-correct marks at all, but your paper is perfect. You won't get full points. On the other hand, you turn in a problem set with a lot of problems missed, but you self-correct everything, right on, full credit. That's what I want you to do. If you have questions on this material, please reach out to me. You can also reach out to the AVID/LSC Center above the library at Mount Hood. They can help you as well. Should be no big deal. You'll turn this in at the beginning of your lab period, along with maybe last week's labs. Should be good to go. Before we start problem set number 4, though, I do want to tell you about a couple of handouts which will be very helpful to you while completing this. The first of one, that's probably the most important one, is called the Geometry and Polarity Guide. And I actually have a dedicated URL for this, mhchem.org/GOPO. All right. And this will have all the different names of the electron pair geometries, the molecular geometries, as well as bond angles, polarities, stuff like that. Pretty cool. You will also need a table of electronegativity values. This is located at the end of problem set number 4, but if you don't have any of these things, of course, let me know. But you will need these as you go through the problems, in addition to the periodic table. Okay, let's see what problem set number 4 has to offer. This first question is just to make sure you know how to find how many electrons can be used in making a molecule. And the electrons that are used in making a molecule are called the valence electrons. They're the outermost electrons. The innermost electrons are held too close to the nucleus to do anything, but those outer electrons can absolutely make that happen. So I filled out the first row for you there. It's for nitrogen. And on the periodic table, if you can look at it, that's cool. Nitrogen is in group 5A. All right. And just so you know, nitrogen is number 7. That's the atomic number. 7 means it has a total of 7 electrons. Well, of those 7 electrons, only 5 of them are available for bonding in molecules. Those are the valence electrons. And the valence electron number equals the group number. So group 5A means 5 electrons for valence electrons and bonding. That would be the same number of valence electrons for phosphorus and arsenic under it. Everything in that column is going to have 5 valence electrons. Now, core electrons are just the electrons that don't react. So you take the total number of electrons in the atom and you subtract the valence electrons. So nitrogen is number 7. So 7 total electrons minus 5 valence electrons, which you get from the group number. 7 minus 5 equals 2. So nitrogen has 2 core electrons that won't be involved with bonding. They just kind of sit there. Now, more than 4 pairs possible is going to be something that'll help us a lot. This is what differentiates our class from some of the lower chemistry classes. You can make more than 4 electron pairs around a central atom if your atom is in the 3rd period and lower. Periods go left to right on the periodic table. So the 2nd period is lithium on the far left through neon on the far right. Nitrogen is one of those. And if it's in the 2nd period or 1st period, you need to put no. Those elements will not make more than 4 pairs. All right. Nitrogen will always have 4 pairs. And then the last column there, less than 4 pairs possible, that's only possible for a few elements, mostly on the left side of the periodic table. Less than 4 pairs possible is possible when you have boron, aluminum, beryllium, those kind of things, but it's very rare for most of the other elements. So nitrogen cannot make systems with more than 4 pairs. It cannot make systems with less than 4 pairs. Nitrogen will always have 4 pairs punchline. All right, so continuing down, carbon then is the next one. And again, just to kind of review everything we've talked about so far, periodic table, you can get mhchem.org/per tab. Group number equals valence electrons, and core electrons is just total electrons minus the valence electrons. So knowing that then, carbon is in group 4A. It's number 6. Group 4A means 4 valence electrons. Core electrons in carbon will be 6, the total number, minus valence electrons 4. That's going to be 2 core electrons. Carbon cannot make more than 4 pairs. It is not third period and lower, and it will not make systems with less than 4 pairs. It's not aluminum, boron, beryllium, stuff like that. So notice that there are some similarities between carbon and nitrogen. They have different valence electrons, but they have the same core electrons, and they can't make more or less than 4 pairs. They'll always make 4 pairs. Chlorine is number 17 on the periodic table, and it's in group 7A. So 7A means 7 valence electrons, and 17 total electrons minus 7 valence electrons, 10 core electrons. Now, chlorine is in the third period, and that means that chlorine can make more than 4 pairs. So when we're drawing Lewis structures, sometimes chlorine will have more than just the tetrahedron, and we'll talk about that in a little bit. But for right now, because chlorine is third period and lower, it can make more than 4 pairs. However, less than 4 pairs, no way. Chlorine loves electrons so much that it won't make less than 4 pairs. It always wants to have at least 4 pairs, and sometimes even more than that. Good to go. Now, krypton is a noble gas, and people thought krypton couldn't make compounds, i.e. we wouldn't be drawing Lewis structures with them. However, in the 1950s and 60s, krypton reacted with fluorine to make some compounds that could be characterized. So actually, krypton is an element that does make compounds. They're very reactive compounds, but they can be made. But we can all use the same kind of rules on all of this. So krypton is number 36 on the periodic table. Krypton is in group 8A, so that means 8 valence electrons. Core electrons, total minus valence, 36 minus 8 is 28 core electrons, so a lot of them just sit there. Krypton is definitely third period and lower, so it can make more than 4 pairs, but less than 4 pairs, no. Always going to have at least 4 pairs, at least so far as scientists have seen. Silicon. All right, next one on this list. Silicon is number 14 on the periodic table, and it's in group 4A. So that means it's going to have 4 valence electrons. Anything in group 4A may have 4 valence electrons. 14 total electrons minus 4 valence means 10 core electrons. Silicon can make more than 4 pairs, but like the other ones so far, it will not have less than 4 pairs. It will always have at least 4 pairs. Selenium, number 34 on the periodic table, and selenium is also group 6A on the periodic table. So 6A means it's going to have 6 valence electrons. 34 total electrons minus 6 valence means it's going to have 28 core electrons. Selenium is definitely third period and lower. Yes, it can have more than 4 pairs, but again, it's not going to have less than 4 pairs. Only a few elements can actually have less than 4 pairs. A lot of them have more than 4 pairs possible, but not less. By the way, just because it's possible doesn't mean they will have more than 4 pairs. They might be totally happy with 4 pairs. It kind of depends on the electrons, as we're going to see. But at least this way we can know which ones can have more than 4 pairs. And then finally, aluminum's number 13. 13 is the total electrons, but it's in group 3A. That means 3 valence electrons. So for this one, group 3A means 3 valence electrons. 13 total electrons minus 3 valence means 10 core electrons. Yes, it can make more than 4 pairs. It's rare, but it does happen. And most importantly, aluminum is the only one on this list that can have less than 4 pairs. Aluminum and boron and beryllium sometimes do their own thing, definitely. So if you can see these patterns, you'll be good to go for building Lewis structures, and we'll talk about how to do that in the next problem. So number 4, draw a Lewis structure for each of the following molecules or ions. Okay, so this is where now you've got to start drawing the Lewis structures, and this is the real focus now of all of the classes, all these sections we're going through right now. So I'm going to do my best here with my technology, and I'm going to try and draw the Lewis structures for some of these so you can kind of see what's going on. I'd like to do at least the first 3. So let's start with CS2, carbon disulfide. If I said, okay, draw the Lewis structure, well, here's what I would do. First thing, figure out valence electrons. Carbon is 4 and sulfur is 6, and there's 2 of them. So if you count that up, 4 plus 12, that's 16 valence electrons. But usually in these Lewis diagrams, we think about them as pairs. So I'm going to divide by 2. 8 pairs of electrons for this molecule. Then you can start putting the central atom down. It's usually the first atom listed. It's always the atom of smaller electronegativity. Carbon is a really good central atom, as you're going to see. So we'll put the sulfurs then on the outside of carbon. The first thing you want to do is connect the outer atoms to the inner atoms. You don't want the atoms to float off into space. So we draw a single bond, which is a sigma bond we talked about in lecture. That just connects the outer atoms to the inner atoms, so they won't float away. Each of those lines is a pair, so I've now used up 2 of my pairs, and I have 6 pairs left. And with the remaining pairs, you put them on the outside atoms first, and if you have any left over, you put them on the middle atom. So you can see there, I just placed the 6 pairs around. I put 3 lone pairs on each sulfur. Sulfur now has a total of 4 pairs, 3 lone pairs, and a bonding pair. The goal most of the time for these is to get 4 pairs around it. That's the octet. And right now, both sulfurs have an octet, so they're happy. But before you go away from the structure, you've got to look at the central atom. Carbon always has to have an octet as well. And carbon right now only has 2 pairs of 4. It's got 2 bonding pairs, but that's it. So this structure is not happy yet. So what we can do then is take away a lone pair from each sulfur, and you make a second bond between the carbon and sulfur. So again, these lines down here are no more. You then have double bonds between the carbons and the sulfurs. And at first you might say, hey, wait a minute, aren't you cheating sulfur? But sulfur still has an octet. Sulfur now has 2 lone pairs and 2 bonding pairs for 4 pairs total, and both of them are that way. But now carbon's happy too. So carbon has 4 bonding pairs. That gives its octet that it's all worried about. So this is the structure then for CS2. Carbon in the middle with 2 double bonds to sulfur atoms. Everybody's got an octet. Everybody's happy. First Lewis structure down. Woohoo! All right. Let's look at the next one there. BF4 -1. So again, same kind of game as before. Start by counting the valence electrons. So boron is in group 3. Each fluorine is 7, and there's 4 of them. Now, a -1 means it has an extra electron. So you add the -1 as an extra electron. It feels weird, I know, negative and you're adding, right? Opposite sides. But in chemistry, that -1 just means an extra electron. That's why you add the extra one there. If it was a positive ion, you would take away an electron, something like that. Anyway, count up the number of electrons. You got 28 from the fluorines plus 4. So that's 32 valence electrons or 16 pairs. And like before, put the central atom in the middle. It's usually the first atom listed. Boron is certainly less electronegative than fluorine, which is the most electronegative. We'll see later. Boron definitely goes in the middle. We'll put the fluorines around the outside. You have to connect the fluorines to the central atom to keep them from running away. That's 4 of my 16 pairs, so I have 12 pairs left. and then we'll make octets around the outer atoms first, and if there's anything left over, we'll put it in the middle. Well, an octet means give each of the fluorines 3 pairs, so you can see that fluorine has 3 lone pairs and a bonding pair for 4 pairs total. Keep going. 1, 2, 3. 1, 2, 3. 1, 2, 3. And at this point, I've distributed all 12 of my electrons. I'm out of electrons. Make sure everything has an octet. Fluorine is definitely good to go. Boron has 4 bonding pairs around it, so it also has its happy space. It's got all of its electrons. This Lewis structure is good to go. Sometimes when it comes to ions, you'll see either a partial kind of bracket like that, like I've drawn right there, or sometimes you'll see a complete square bracket just to show that there's an extra electron inside there. That's a good call if you have an ionic form. Cool. The next one is nitrite, NO2 minus. Nitrite is the bad stuff in meat hot dogs. If you eat meat hot dogs, you might want to look up what nitrite's all about, but I'm not going to preach as a vegetarian. Sorry, fascist instructor. Anyway, babbling once again. Nitrite, NO2 minus, is also a polyatomic ion, so we can build polyatomic ions. It's pretty cool. But again, just like before, let's start counting electrons. Nitrogen is 5, oxygen is 6, and there's 2 of them. And like we did in the last one, negative means to add. So we're going to add 1 more electron to it. We've got 5 plus 12 plus 1. I believe that's 18 electrons. Divide by 2 would be 9 pairs. Nitrogen goes in the middle. Oxygen's on the outside. Connect the outer atoms to the inner atoms using a pair of electrons, a bonding pair. So that's 2 of them. So I've got 7 pairs left. You then put the lone pair electrons on the outside atoms first, and if there's any left over, put them on the inside. So oxygen, like fluorine and the rest of them, wants to have a filled octet. So that 3 lone pairs of electrons will give it an octet. I'll do the same thing on the other side. 4, 5, 6. That gives that oxygen an octet. And I do have 1 lone pair left over to put on the nitrogen. So at this point, I've used up my 7 extra pairs of electrons. I need to analyze now to see if everything has an octet. And you can see again that oxygen definitely has the octet. They've got 3 lone pairs and a bonding pair, so 4 pairs total means an octet. But nitrogen has 2 bonding pairs and a lone pair. That's 3 pairs, and you need to have 4. So something really interesting happens here. You need to give nitrogen another pair of electrons. So like we did earlier, let's take, for example, this lone pair, and let's make a double bond right there. And this is really cool because now nitrogen has 1, 2, 3 bonding pairs and a lone pair. It's got its octet. The oxygen has, on the left, has 2 lone pairs and 2 bonding pairs. It's got an octet. The oxygen on the right still has the octet. So this is definitely a cool structure. But I know somebody watching this video says, hey, wait a minute, why didn't you take the lone pair from the other oxygen? So notice this new structure I've drawn. It's the same, oops, I forgot the lone pair. It's the same as the last one, but instead of making a double bond in the left-hand oxygen, we're making a double bond in the right-hand oxygen. And you can see that all the electrons here are happy, all the atoms have octets, blah, blah, blah. In this kind of Lewis structure, both structures are correct. This is an example of what's called resonance, all right? And resonance means you have a choice of where the lone pair is turned into a double bond, all right? There's no energy reason for picking the left oxygen versus the right oxygen. They're totally the same thing. When you see a resonance form, it's really best to draw both versions of the structure, all right? Because resonance shows that you know that there's a choice where these things go. It'll affect the bond order. We'll talk about that later. Pretty important kind of thing. So nitrite here with a little -1 to show it's a charge does have a resonance form, and I do recommend that you draw all resonance forms, especially in the first couple sections. After a while we'll get a little bit lazier about it, but for right now make sure that you show me that you know that there's resonance forms around. The last one there, SOCl2, sulfur is group 6, oxygen is group 6, chlorine is 7, and there's 2 of them, so 14 plus 6, 20 plus 6 more, 26 valence electrons or 13 pairs. Sulfur definitely less electronegative relative to oxygen and chlorine. I'll put them over there. I'll connect the outer atoms to the inner atoms using a bonding pair. That's 3 of my 13. I've got 10 more to go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1 lone pair on the sulfur. This form is okay as is. Everything has an octet, all right? The oxygen has 3 lone pairs and a bonding pair, just like the chlorines. And sulfur has a lone pair and 3 bonding pairs. So everything has an octet. However, later on, we're going to look at formal charges. And you get a little bit better formal charges when you draw a double bond to oxygen. So if you do that, this is the best structure. There's nothing wrong with the one above it, all right? It's pretty good, but you get an even better structure if you draw a double bond O. We're going to talk more about formal charges in a little bit, but I just want you to keep that in the back of your mind. Both versions are okay, but a double bonded O is better. And sulfur is period 3 and lower, so sulfur can go beyond the octet. The first structure I drew, sulfur had 3 bonding pairs and a lone pair, 4 pairs total, and that's fine. But the bottom structure with a double bond O, now sulfur has 4 bonding pairs and another lone pair, so that's 5 pairs total. Sulfur can do that because it's period 3 and lower. So keep that in the back of your mind about formal charges. Now, all of my drawings are pretty bad. I apologize. Here are better computer-generated versions to show you all the differences and stuff. We'll talk more about formal charges later on stuff, so hang tight, but hopefully this will at least get you started in the wonderful world of drawing Lewis structures. Draw a Lewis structure for each of the following molecules or ions, okay? So this question is actually very similar to number 4 we just did, but the difference here now is we're going to start looking at some trigonal bipyramid and octahedral structures. And again, this is what makes Chem 222 different than our Chem 100 classes at Mount Hood. These do exist. There's quite a few of them. They're maybe not as important because they're not as classic organic chemistry / biochemistry, but they are pretty cool and they're not too hard to do. So let me show you some examples of how this works. BRF5. So bromine is in group 7. And fluorine, which is also group 7, and there's 5 of them. I'm counting the valence electrons, by the way. So 7 plus 35, that's 42 valence electrons, or 21 pairs. And bromine will be in the middle. It's less electronegative than fluorine. Fluorine is the most electronegative of all. I'll put the fluorines around the outside, and there's 5 of them, so it's a little bit different, but nothing you can't do. I need to connect the outer atoms to the inner atoms using a bonding pair. So I'm going to draw a bonding pair between all 5 of those. I now have used up 5 of my pairs. I have 16 pairs left. And now I'm going to put lone pairs on the outside atoms first. And if I have any left over, I'll put them on the inside. So fluorine is in the second period. It can only handle an octet. So giving it 3 lone pairs plus a bonding pair makes it totally happy. That's 3 of my 16. 4, 5, 6 to do that fluorine. 7, 8, 9 to do that fluorine, 10, 11, 12, 13, 14, 15. But I have 16 to distribute. So what that means, this bromine has a lone pair on it. And I put this problem up here because it is so freaking critical that you count your valence electrons. After a while, you'll get kind of, oh, I'm good, I'm bad and stuff, I can do this. And you'll just draw bromine with the 5 fluorines around it, give them an octet and move on. But don't do that. A lot of these have a hidden lone pair around it, like this one right here. Bromine is in an octahedral environment. It has 5 bonding pairs and a lone pair, 6 pairs total. That's why BRF5 is an octahedral thing. So if you put trigonal bipyramid, it's basically just a reminder, man, count the electrons, all right? It will come back to haunt you if you don't. It's really important. Okay, next one, IF3. So iodine is in group 7. Fluorine is also in group 7, and there's 3 of them. So counting up those electrons, that's 28 electrons. Divide that by 2, 14 pairs. Again, fluorine never goes in the middle since it's most electronegative of all. I'll put the 3 fluorines around it, the iodine, like that. I'll connect the outer to the inner atoms. That's 3 of my 14 pairs, so I've got 11 left. Lone pairs on the fluorine to give them an octet. And that used up 9 of my pairs. So I have 2 pairs left here. So iodine is not going to have just 1 lone pair. It's going to have 2 lone pairs on it. Iodine has 3 bonding pairs and 2 lone pairs, 5 pairs total. This iodine is in a trigonal bipyramid geometry. We'll talk about that more in a little bit. So again, 6 pairs like on the BRF5 is octahedral. 5 pairs like IF3 right here will be trigonal bipyramid. So just be aware there's some kind of subtle differences for these things. But again, count up the electrons, you're good to go. IBr2 minus 1. Iodine is 7. Bromine is also 7. And there's 2 of them. And we're going to add 1 because of that negative 1. Remember, negative means to add and positive means to subtract. I know it's weird. 21 plus 1 would be 22 valence electrons or 11 pairs. We'll put iodine in the middle of the bromines. We'll connect the outer atoms to the inner atoms with a pair. Put lone pairs around the outside first. I've now used up 1, 2, 3, 4, 5, 6, 7, 8. I have 11 pairs total. So 1, 2, 3 lone pairs around the iodine, even more than last time. Whoa! Oh, and I should put the little negative 1 thing right there. Anyway, again, just shows you how critical it is to count up the electrons. Again, all of these atoms, bromine, iodine, etc., they're capable of making more than 4 pairs because they're period 3 and lower. Period 3, again, is sodium through argon on the periodic table, and Br and I are certainly lower than that. We could never make a compound like IBr2 minus with fluorine in the middle, for example. Fluorine, carbon, nitrogen, they are limited to 4 pairs. But with these kind, you can kind of get kind of crazy. Woohoo! Crazy in my world is pretty lame, I know. But anyway, I digress. Okay, last one. BRF2 plus, bromine group 7, fluorine also 7, and there's 2 of them. And here's a positive one. So we add for the negatives like we did in the last one, but here I'm actually going to subtract 1 because a positive charge means it's deficient in electrons. We have to take 1 away. It's, I know, totally counterintuitive. So 21 minus 1 would be 20 valence electrons or 10 pairs. So again, bromine in the middle, fluorines on the outside. Connect the fluorines to the bromine in the middle. That's 2 of the pairs. I got 8 left. 1, 2, 3, 4, 5, 6, 7, 8. So this positive species, the bromine, has 2 bonding pairs and 2 lone pairs, 4 pairs total. So this one actually is not the octahedral or trigonal bipyramid. It's a regular 4-coordinate tetrahedral kind of thing. So again, it's hard to say by just looking at a structure, at least at first, how they're going to look. But if you count the valence electrons up and stuff, you're good to go. Now, my drawings are pretty cheesy, so here's examples of what they look like in a computer-generated world. Yes, they're a little bit nicer. I have horrible handwriting. I really apologize, but this will then show more formally what they look like, and you can see the differences in the electrons. They're using the complete square brackets to show the charge, which is fantastic. Draw a Lewis structure for each of the molecules or ions. Describe the electron pair geometry and the molecular geometry around the central atom. Okay, cool. So this is the first question now where we're going to interpret the Lewis structure, and we're going to pull out those terms I was using in the last problems, like tetrahedral, octahedral, trigonal bipyramid, stuff like that. The first goal on all of these is you need to draw a Lewis structure. And from the Lewis structure, you can then interpret it using the geometry and polarity guide to figure out what both the electron pair geometry is and the molecular geometry is. So ClF2, and I want to point this out. ClF2 plus is what this molecule is. Once in a while, I have people that think it's C1 or ClF2, and I just want to point it out that, yeah, this is very chlorine can be a central atom. If you are ever uncertain on a quiz or exam, if I'm asking for a question that's a Cl or Ci, by all means, feel free to ask me. All right, that is absolutely fair game. I want you to know what the question is before I grade anything, right? So this is a chlorine with 2 fluorines around it and a positive 1 charge. When you draw the Lewis structure for ClF2+, and I'll let you do this on your own, this is what it comes out to be. To figure out the EPG and Mg terms, and again, EPG is electron pair geometry and Mg is molecular geometry, you look at the central atom, the chlorine in this case, and your chlorine has 2 bonding pairs, i.e. a bonding pair to each fluorine, and 2 lone pairs. So it has 4 pairs total around the chlorine. Every time you have 4 pairs around a central atom, the electron pair geometry is tetrahedral, all right? And we're going to see that a lot. So 4 pairs, whether they're bonding pairs, lone pairs, whatever, tetrahedral electron pair geometry. And the molecular geometry here is actually going to be bent. Tetrahedral angles are about 109. Now, the drawing I have here shows the FCLF as being 180 degrees apart from each other. Lewis structures by themselves don't have usually any information what the geometry looks like. This kind of keeps the chemists who aren't artists, all right, from having to draw things in kind of correct angles and stuff like that. So Lewis structures will usually not show any geometry. With my poor drawing skills, if I was to try and show what the geometry is, it would look something like that. All right. This FCLF angle is supposed to be about 109. I think I made it a little bit bigger than 109, but hopefully you kind of get the idea. This structure that's listed is just the Lewis structure. So again, Lewis structures do not, by default, have any information on the geometry, what it quote-unquote looks like in space. But using electron pair geometry, molecular geometry terms, which come from VSEPR, the valence shell electron pair repulsion theory, that's what allows us to figure this out. At this point, what I'd like you to be able to do is look at the central atom and count the number of clouds, number of lone pairs, bonding pairs, etc. And from there, you can go to the geometry and polarity guide, look up the 4 cloud area. All right, so it starts with 2 clouds, then goes to 3 clouds, and finally 4 clouds. And under 4 clouds, there will be sections for number of bonding pairs and lone pairs. And if you have 2 lone pairs and 2 bonds to atoms, and bonds to atoms are bonding pairs, then if you go over in that column, you'll see it's tetrahedral for the EPG and bent for the molecular geometry. So please make sure you know how to do that before looking at the other questions in this problem set, all right? Pause the video right now and go back to your geometry polarity guide and see where tetrahedral and bent come from, because without doing that, you're going to be at a disadvantage for the remaining problems. If you really don't get it, then man, email me, all right? Send me a screenshot, tell me what you're thinking. I'll try to get back to you and we'll figure out what's going on. Moving on then, the second one one, SnCl3. When you draw out the Lewis structure, that's what it is. The tin has 3 bonds to atoms and a lone pair. It's a -1 ion. Well, around the tin, the central atom, 3 clouds to atoms and 1 lone pair cloud, 4 clouds total. So again, electron pair geometry, tetrahedral. The molecular geometry, when there's 1 lone pair and 3 pairs and 3 bonds to atoms, is called trigonal pyramid. All right, and trigonal pyramid is one we're going to see quite a bit. You can abbreviate trigonal pyramid as trig-pyr. All right, that would be okay, but do not call it just trig. There's trigonal planar and there's trigonal bipyramid. So calling it trig by itself is not enough. Also, don't call it pyramidal. In our Chem 222 world, there's a trigonal pyramid and there's also a square pyramid. So you've got to put down trig-pyr to make sure that it's clear. All right, you put down anything else, you'll probably get in trouble. If in doubt, just put the whole thing down, obviously, right? It's better. Okay, next one, BCl3. Boron is one of the few atoms that can be under an octet. So we've made a big deal earlier about things that go beyond the octet. Boron and beryllium and aluminum, sometimes gallium, they can actually go under the octet. So boron with 3 chlorines around it is a happy molecule, all right? And again, you couldn't do this for carbon or nitrogen or oxygen. This only applies when you have boron, aluminum, beryllium sometimes, gallium sometimes. But anyway, boron has 3 clouds to atoms around it, 3 clouds total. That's going to be trigonal planar electron pair geometry. And because boron doesn't have any lone pairs on it, the molecular geometry and the electron pair geometry are the same, trigonal planar, all right? So a lot of things come out here, all right? Boron, beryllium, aluminum, gallium can go under 4. This is an example. Sometimes they will have 4, but in this case, it's definitely under 4. Another thing is that if there are no lone pairs on the central atom, the EPG and Mg will be the same term. The last one is carbon disulfide, and this is one we drew earlier. It's got double bonds to the sulfurs. And I put this up here because a double bond is like one big cloud, all right? You don't break a double bond into 2 clouds. A double bond is 1 cloud. A triple bond is also 1 cloud. So around that central carbon, you have 2 clouds, a cloud to the sulfur on the left, a cloud to the sulfur on the right. 2 clouds means the electron pair geometry is going to be linear, if you look in the geometry and polarity guide. And then it also, because there's no lone pairs, molecular geometry and EPG will be the same, both linear. In the geometry and polarity guide, it'll say things about symmetric and asymmetric. Don't worry about that right now. Symmetric and asymmetric helps with polarity, which we'll talk about later. But for right now, I'm hoping you can get these terms out of the geometry and polarity guide. I wrote the guide, so I'm a little biased. You don't have to use the guide. It really is okay. However, I think it will make your life easier, so I do encourage it, but of course, it's your call. Draw a Lewis structure for each of the following molecules or ions. Describe the electron pair geometry and molecular geometry around the central atom. Okay, so this problem is a lot like the last problem, only with this problem, we're going to look at some examples where we get into the octahedral and trigonal bipyramid system. So I'm going to assume that you can draw the Lewis structures by yourself, and then you can then use the Lewis structure to interpret what the EPG and Mg will be using the geometry polarity guide or something like that. So the first one, silicon, is in the middle of 6 fluorines. Silicon here has a -2 charge, so that's what the brackets are for. However, the important part here is that because silicon is surrounded by 6 bonding clouds of electrons, that makes the EPG octahedral. Anytime you have 6 clouds, whether they be bonding pairs or lone pairs, it's going to be octahedral. And there are no lone pairs around silicon, so the EPG and the Mg are the same. They're both octahedral. The next one, PF5. When you draw out the Lewis structure, phosphorus is in the middle of 5 fluorines. Again, notice these are both going beyond the octet because they are in period 3 and lower, so they can have more than 4, and they are certainly exhibiting more than 4 in both of these. Anyway, back to PF5, phosphorus in the middle of 5 fluorines, 5 clouds. 5 clouds means electron pair geometry, trigonal bipyramid. And the molecular geometry will also be trigonal bipyramid because there are no lone pairs around phosphorus. The next one is kind of a tricky one, SF4. We're going to do a lot of tetrahedral carbons where there's 4 atoms around a carbon, and so automatically people start thinking, oh, SF4, that's probably going to be tetrahedral as well, and move on. However, if you look on the periodic table, carbon and sulfur are in different groups. Sulfur actually has 2 more electrons than carbon, so it does not work to put SF4 in a tetrahedral environment. So to figure out what's going on here, I would add up the number of electrons in SF4. So sulfur is 6, fluorine is 7, and there's 4 of them. That's 34 valence electrons, or 17 pairs. And because of that 17th pair, sulfur is going to have a lone pair on it. So sulfur has 4 bonds to atoms and a 5th lone pair, 5 pairs total. This is not tetrahedral, it's trigonal bipyramid. Remember, a lot of these will have lone pairs on them, so make sure you count up the number of electrons. If the trigonal bipyramid geometry has 1 lone pair, it ends up being what's called the seesaw molecular geometry. And where the seesaw comes from, if you use your imagination a little bit, it does kind of look like a seesaw. The lone pair is in the plane of the molecule. I circled the lone pair right there, not very good. But anyway, it kind of looks like one of the seesaws if you ever played on as a kid, and like I would be sitting here and then someone else would be sitting there and you rock back and forth. Anyway, if you get it, cool. If you don't worry about it. My drawings that are horrible don't help anything either, but that's where the seesaw comes from. Chemists are lame, whatever you want to use. It's a seesaw. Move on. All right. The geometry and polarity guide helps out a lot, obviously. And then the last one, XeF4. Count your electrons. It's also not tetrahedral. Xenon has 2 lone pairs around it. 2 lone pairs plus 4 clouds to fluorine, 6 pairs total, octahedral. And if you have an octahedral electron pair geometry with 2 lone pairs around it, this becomes square planar for the molecular geometry. Notice how there's square planar and there's also trigonal planar we saw earlier, so don't call either one of these just planar. And again, there's trigonal bipyramid, trigonal planar, trigonal pyramid, so you've got to include lots of information on these. Anyway, punchline here, make sure you count up your valence electrons because they will not steer you wrong. Give approximate values for the indicated bond angles, and there's basically 3 questions. The first one is about SCl2, the second one is about N2O, and the third one is for that phenylalanine structure there on the right. Okay, so punchline for basically all the problems in this problem set, draw the Lewis structure and then go through and interpret at least the electron pair geometry. The electron pair geometry will help you figure out bond angles, all right, because most of the time a tetrahedral bond angle is about 109. A trigonal planar is about 120. Linear would be 180, stuff like that. So for SCl2, the first thing you got to do is draw the Lewis structure. And when you do that, SCl2 initially looks like this structure right here. Now, when you draw ClSCl, all right, it looks like it's 180 degrees flat. But like we talked about earlier, you look for the electron pair geometry of the sulfur, the central atom. 2 lone pairs, 2 bonding pairs, 4 clouds total. That's an electron pair geometry which is tetrahedral, and all tetrahedral angles are about 109 degrees. So the drawings again of Lewis structures will lie to you often. You have to be smart enough to interpret the electronic environment of the atom to figure out what these bond angles are. Technically, mathematically, tetrahedrons will be 109.5 degrees. And if you put that down, honestly, that's fine. In the real world, lone pairs squish the atoms a little closer to each other. Lone pairs are big negative areas of energy. So probably the ClSCl angle would be less than 109. I would guess like maybe 105 degrees, all right? If you look this up on Google, you might have a weird answer. I don't care about any of those numbers. If you put down just 109, honestly, that's fine. If you put down down 100 degrees or 111 degrees, I might get weirded out a little bit as your instructor. But if you put a number that's close to 109, honestly, that's fantastic. Okay, the second one, N2O, dinitrogen monoxide, is kind of fun. That was actually the NOS in the Fast and the Furious movies, if that's a thing you watch. If you don't, you have better watching skills than I do. But anyway, N2O is just a molecule and stuff. It's also laughing gas, which is kind of fun. So for this one, you got to draw the Lewis structure. Now, N2O has many different resonance forms, and I put the three that people usually talk about right there. You can see the top one there has nitrogen with 2 double bonds. The second one has a triple bond to the first nitrogen and an oxygen single bond. And the last one has a triple bond oxygen and a single bond to nitrogen. All three of those structures are 2 cloud systems, all right? Double bonds, triple bonds, and single bonds all count as 1 cloud. So a double doesn't mean 2 clouds. Double is just 1 cloud. And same thing for triple. Triple's not 3 clouds. It's just 1 cloud. So around all 3 of those structures, regardless of which one, or if you drew all of them, you pick, they're all going to have 2 clouds and 2 clouds only. That's going to be a linear electron pair geometry. So those angles literally are 180 degrees. In SCl2, you can see it was drawn flat. That wasn't 180. That's like 109. But in this one, you actually do have 180 degrees flat across. Kind of cool. Now for the last one up there, that phenylalanine, what you need to do is look at the central atom that the angle is located at. And from the central atom, you can interpret the electron pair geometry to get the right name. So for example, on A, the central atom was tetrahedral. If we see tetrahedrals in phenylalanine, they're going to be 109, etc., etc. In the upper right corner, this is a line structure for the atom, for this molecule. And we're going to see this a lot in the upcoming areas. Each vertice on that molecule is a carbon atom. So you can see that in angle number 1, there's a carbon down there. It's connected to the hydrogen, which you see. It has a single bond to the right carbon, and there's a double bond to the carbon in the lower left. Now, carbon always likes to have 4 bonds. That carbon right there has 4 bonds. All right, it's hydrogen, a single bond to carbon, and a double bond to the other carbon. But if you look at the carbon in the lower left there of the one, the carbon has a double to the one we're talking about and a single bond below. That's only 3 clouds. This carbon has a hidden hydrogen right there. The hip chemist knows that carbon always has 4 bonds. That's the octet, really important. So there's like an invisible hydrogen there. There's also an invisible hydrogen there and there and there. But the carbon connected to the CH2 on the right, that already has 4 bonds. That one's not going to have any more carbon. We'll see this more and more as we get into organic chemistry. But anyway, now that we know what the atoms are, angle 1 is an HCC angle, and that carbon in the middle has a double and 2 singles. That's 3 clouds total. 3 clouds means trigonal planar. Angle 1 is going to be 120 degrees. Oh, here's the picture showing the carbons and stuff like that too, if that's easier. Angle number 2, those dark black kind of wedges, they're called, mean that the hydrogens are coming out of the screen at us. All right, it's trying to show geometry. It doesn't show the geometry very well, in my opinion, but that's what it's trying to show. Regardless, angle 2, that central carbon, has 4 bonds around it. 2 bonds to those hydrogens with the black wedges and 2 single bonds to the carbons as well. So 4 bonds total. That's going to be 109 degrees / tetrahedral. All right. Carbon in angle number 3 has a double bond O above, if you will, an oxygen single bond to the right, and a single bond carbon to the left. So a double and 2 singles, that's 3 clouds total. That's trigonal planar. And just like angle 1, it's going to be 120 degrees. Angle 4 is an oxygen in the middle with 2 lone pairs and 2 single bonds, 4 clouds total. It looks like like it's 180 degrees, but remember our drawings are lying to us here. That's not 180 degrees. That's tetrahedral, 109 degrees for that one as well. And finally, angle number 5 is a hydrogen-nitrogen hydrogen. Nitrogen, the central atom, 3 bonds to atoms, and a lone pair, 4 clouds total, 109 degrees. So you can interpret now structures of anything by looking at the central atoms, and that's a real powerful tool when it comes to these. If you look at something as big as like DNA, all right, that monster molecule is just huge, man, but no problem. You can look at individual atoms, look at the bonds around it. You can figure out approximate bond angles, stuff like that. It's a pretty cool technique. Determine the formal charge on each atom of the following molecules or ions, and we'll look at the formate ion, HCO2-1. We'll look at formic acid, which looks a lot like formate ion, hint, hint. And finally, we'll look at carbon dioxide. We'll look at 2 resonance forms, and we'll predict which resonance form will be more stable. So first, of course, you have to ask, what the heck is formal charge? And that's totally legit. Formal charge equals group number minus lone pair electrons minus number of bonds. So if you're talking about lone pair electrons and numbers of bonds, you of course have to draw the Lewis structure out first. And from that, then you can figure out what the formal charges are. This is a picture of the formate ion when you draw it out. Carbon in the middle, hydrogen never in the middle, oxygen more electronegative on the outside. Initially, when you draw it, you have 2 oxygens with 3 lone pairs around them, but carbon needs 4, so you have to make a double bond somewhere. All right, and so I picked it from the top one. You could have just as easily picked the double bond from the right oxygen. It doesn't matter. But what I'd like to do now is focus on the formal charges. Hydrogen is group number 1, and you can see that the hydrogen there has no lone pair electrons. All right, no problems. And then you can either do 1/2 bonding pair electrons, or you can just take number of bonds. So if you're thinking about number of bonding electrons, each line is 2 electrons, and half of that, 1/2 of 2, would be what you'd want to do. But I would prefer you just subtract the number of bonds. So I would go 1 minus 0 minus 1. Either way works. You should get a formal charge of 0. Carbon, same kind of thing. Carbon is in group 4. It has no lone pair electrons. I would subtract 4, the 4 bonds around carbon, but you can also go 1/2, 8, the bonding pair electrons. Either way, carbon also has a formal charge of 0. Now, let's do the top oxygen, the double bonded oxygen first. So oxygen group number 6, it has 4 lone pair electrons. We're subtracting all the lone pair electrons, and then minus 2 bonds, or minus 1/2 of 4, either way, formal charge of 0. And now the oxygen with the single bond, group number of oxygen still 6, subtract the 6 lone pair electrons, minus 1 bond, or minus 1/2 of 2, either way, formal charge -1. Now, when you do the formal charge analysis, you should step back for a second and see if your answers make sense. The sum of all the formal charges will equal the charge on the molecule, if any. And this thing does have a charge. It's -1. So you can see that 0 plus 0 plus 0 plus -1 is -1. That means that this is a good Lewis structure. It also means we've done our formal charge analysis right, which is cool. That -1 is important because if you have something positive going to attack it, the positive charge will look for that negative oxygen, the singly bonded oxygen, to make a bond. So the charges sometimes will help you to make predictions as to what's happening. Now, in reality, that's a resonating bond. You can have a double bond on the top. You can also have a double bond to the right. It goes back and forth, but somewhere there's going to be a -1 charge on it, and that's where the positive things will attack. And when you turn formate into formic acid, that's exactly what happens. That hydrogen, which is a plus, H plus, comes in and it attacks the oxygen with the -1 charge. And so you can see here all the different formal charges. The first H, the carbon, the double bond oxygen, they're still all 0. That's no problem. But by having an H plus attack that O negative 1 formal charge, now both of those go to 0. So formic acid is neutral, and all the formal charges should go to 0, which is really cool. So that would be a good Lewis structure. Formic acid, if it loses the acidic hydrogen, becomes formate, and formate plus an acidic hydrogen becomes formic acid. But the real value of formal charges is in identifying which resonance form is better. So for carbon dioxide, there's actually three different ways, I guess technically, that you can draw the molecule. The main way is this one right here, C with 2 double bonds O. But you can also have a resonance form where there's a triple bond and a single bond, and it could be one side or the other. It's hard to say. Now, carbon, still group number 4, minus 4 bonds, regardless of which structure, and no lone pair electrons. Carbon's going to be 0 on both of them. But notice here how the oxygen with 3 lone pairs and a single bond has a negative 1 charge, just like the last oxygen did right over here with the formate ion. All right, same thing. And you can also have in the structure on the right a positive 1 oxygen. Oxygen group number 6, subtracting 2 lone pair electrons, minus 3 bonds, or minus 1/2 of 6, either way, positive 1. Now, the carbon dioxide resonance form on the right is still a valid resonance form because the sum of those formal charges, -1 plus 0 plus 1, equals 0. CO2 is neutral, so that's okay. However, as a chemist now, you can say that the first structure, the one on the left with 2 double bonds, is a better structure. The more zeros you have, the more stable the molecule is. So CO2 is definitely predominantly 2 double bonds. Now, in biology, CO2 reacts with water to make formic acid, carbonic acid, H2CO3. That can only happen with the resonance structure on the right. The H2O comes in, it sees the positives and negatives, and it attacks from there. That's where carbonic acid basically forms. It would be, I would argue, very, very difficult for CO2 and water to make carbonic acid using the resonance structure on the right. The positive and negative ones are kind of like beacons in the night, and things that are negative or positive, the opposite, will be attracted to negative ones and positive ones in a structure. So the formal charge analysis will tell you which is the best structure. More zeros is better than less zeros. So the structure on the right with a -1 and a +1, not as stable as the one with all zeros. For each of the bonds listed below, tell which atom is the more negatively charged. Use values of electronegativity to support your answer. Okay, so on this question, all right, you really should have the table of electronegativities in front of you. And when you look at that table, fluorine, which is in the upper right part of the periodic table, is the most electronegative of all. And if you compare fluorine to anything, fluorine will be the bigger electronegativity, and that means fluorine will be the negatively charged part of the bond. So on all of these kind of things, the bigger electronegativity means it's going to be negative, and the smaller electronegativity means it's going to be positive. Now, you can also kind of guesstimate some of these, remembering that fluorine is the most electronegative, oxygen is second only to fluorine, and then nitrogen and chlorine are third. Sometimes you can go through and kind of figure out based on their position in the periodic table where it is. But if you have the table, definitely use that. So for C and N, all right, the values of carbon, the electronegativity value is 2.5, and nitrogen is 3. So the more negatively charged atom will be the bigger electronegativity value, 3.0 bigger than 2.5. Nitrogen will be the bigger, more negatively charged atom in this one. Things closer to fluorine were more likely to be the negative one. CNH is something similar, 2.5 versus 2.1. So carbon is bigger. It's going to be more electronegative. Bromine is bigger than carbon electronegativity, so it will be bigger. And oxygen, second only to fluorine, is almost always the negative one. 3.5 is larger. So using those electronegativity values, you can make predictions then what's going to be the negative side, and you can then make predictions as to reactivity, stuff like that. Considering both formal charges and electronegativities, predict on which atom or atoms the positive charge resides in the following cations. And here's several different positive cation species, okay? So what I would do on this problem is first draw the Lewis structure, and then you can look at the formal charges and or the electronegativities to see where the positive charge is going to be. And here's a side note. If you put a positive charge on hydrogen, which can only handle one bond anyway, that's essentially like breaking all electron glue to any other atoms. So H plus will literally float away from the molecule. So on the first two, you really can't put a positive charge on the hydrogen. So here's an example of all four molecules, and this is their Lewis structures. H3O plus, the hydronium ion, is first. The second one, NH4 plus, is ammonium. The second one, NO2 plus, nitrosyl. And then the last one, the NF4 plus molecule. And from there, you can either do formal charges or you can look at electronegativities. The first two, though, like I said, are easy because you can't put a positive charge on the hydrogen and expect it to sit next to the molecule. Those lines that connect hydrogen to the central atom, that's like the glue, all right, that holds hydrogen to them. If you put a positive on a hydrogen, it floats away and you won't have that anymore. So for A, for the first one, hydronium, the hydrogen is going to have a 0 formal charge, and oxygen turns out to be positive 1. Remember, formal charge, group number, minus lone pair electrons, minus bonds. So for oxygen, 6 is the group number, minus 2 lone pair electrons, minus 3 bonds, positive 1. So for the first one, it has to be on the oxygen. The positive charge has to be on the oxygen. Now, oxygen is much more electronegative than hydrogen, but hydrogen, as positive 1 floats away, you wouldn't have H3O plus anymore. All right, hydronium, H3O plus, makes water pretty readily because H plus does float away, and that's another whole game. But if we're going to keep this as hydronium, you must have the positive charge on oxygen. Oxygen hates being positive, but in this molecule, it has to be. So you can do the same kind of thing for the other ones. On ammonium, NH4 plus, all the hydrogens are again 0. Nitrogen is positive 1. And again, nitrogen is more electronegative than hydrogen by far, but if you put that positive on the hydrogen, it floats away. Ammonia, NH3, can be made from ammonium, NH4 plus, if you remove that H plus ion. And that's something that's pretty easy to do, just like hydronium goes to water. But if you want hydronium to stick around, the positive charge must be on nitrogen. Now, the last two are a little bit easier because nitrogen, although electronegative, is nowhere near as electronegative as oxygen or fluorine. So automatically, you can predict that the positive charge is going to be on the nitrogen in both C and D. And that's definitely what you see. The outside atoms of a molecule will almost always have a filled octet. So the oxygens and NO2 plus definitely have a filled octet. That positive charge is going to be on nitrogen, and that makes sense because nitrogen is not as electronegative as oxygen. It should be positive relative to oxygen, and the same thing for fluorine. Fluorine's the most electronegative of all. Nitrogen is definitely going to get that positive charge. Remember, the sum of all the formal charges must equal the ionic charge of the molecule, and since all of these are positive, you have to have something be positive. It's going to be nitrogen in B, C, and D, but on A, it will, of course, be oxygen. None of these atoms are probably that happy with it, but it's kind of how it has to work out to make the molecule. Determine if the following molecules are polar or nonpolar. Use a table of electronegativities to determine the most polar bond in the molecules below. Okay, so there's kind of two questions going on here. The first one is, which of these molecules are polar or nonpolar? And to answer that, we're going to look for symmetric molecules. If a molecule is symmetric, you've got atoms pulling electrons equally but in opposite directions. So during lecture, I was babbling about Arnold Schwarzenegger, who's kind of one of my heroes. Schwarzenegger, I always think of as really tough. He could pull me with my one arm his way, no problem. But if Schwarzenegger had a twin, and the twin was equal to Schwarzenegger, like one twin could pull to my right with my right arm, and one twin could pull to the left with my left arm, and they would pull even but opposite because they're equally strong. So each Michael Schwarzenegger bond is polar, i.e. he's pulling much stronger than I can pull back. However, the Michael to Schwarzenegger molecule would be nonpolar because the pull to the left is canceled by the pull to the right. So we're trying to see which molecules are polar and nonpolar, and that's looking at the whole thing, and we're also going to look at the individual bonds to see which one is most polar. And to see which one is most polar, we'll use those tables of electronegativity. So in my silly example, there would be values of electronegativity for Michael and Schwarzenegger would have a bigger electronegativity, he pulls better. But there might also be, Jean-Claude Van Damme. I'm probably dating myself here, but he's another kind of cool person in my mind. Jean-Claude Van Damme is also tough. He would have a different electronegativity than Schwarzenegger. So Jean-Claude Van Damme would be a different polarity, if you will, than the Michael Schwarzenegger. If that was totally weird, I apologize. Sometimes my examples go a little south on me. Let's look at CS2. All right. So CS2, if you draw out the Lewis structure, we've done it already a couple times. It's a carbon with double bonded sulfurs on both sides. Sulfur is pretty electronegative, all right? But carbon actually is equal in electronegativities to it. So notice here the delta chi value, the change of electronegativity. It's actually 0, all right? So carbon-sulfur bonds are not polar, all right? There's no difference in electronegativity. And because carbon is in the middle of two sulfurs, the sulfur on the left and the sulfur on the right, it's also symmetric. Everything around the carbon is the same. So CS2 is a non-polar molecule, and because delta chi is amazingly 0, which never happens, by the way, but it does happen here, then it's also a non-polar bond. So if delta chi is 0, non-polar, but almost all the times delta chi will not be 0, and that means it's a polar bond. But for the polarity, we look at the whole molecule, draw the Lewis structure out, good to go. Second one, carbon tetrafluoride. Carbon and fluorine have a big delta chi, a big change in electronegativity. So that means the CF bond is definitely polar, all right? Fluorine is pulling a lot stronger. This would be like Schwarzenegger and Michael something. It's a big delta chi gap. So fluorine is very, very strong. It's pulling electrons its way. But the whole molecule is tetrahedral. Everything around the carbon is just fluorine. So everything is symmetric around the carbon. And if everything is symmetric, that means this is going to be a non-polar molecule. So here we have polar bonds, fluorine pulling much more than carbon, but because everything around the carbon is just fluorine, then they're all pulling equal and opposite. This is a symmetric molecule, non-polar CF4. The next one, PCl3. When you draw out the Lewis structure, there's a lone pair on the phosphorus. So the electron pair geometry of PCl3 is tetrahedral. So a lone pair with 3 chlorines, that's not a symmetric environment. So that automatically makes it polar. Now in the last two examples, everything around the central atom was the same. So on carbon with 4 fluorines, that's all the same. Carbon with 2 sulfurs, everything the same. The lone pair is enough to make the symmetry of the molecule break up, and that's going to automatically make it a polar molecule. It's a pretty polar bond. Difference between phosphorus and chlorine is respectable 0.9, so it's polar, although not as polar as the CF bond. The last one, CO, the difference in electronegativities is 1, so that means it's pretty polar. Oxygen pulls pretty strong relative to carbon. Carbon and oxygen are the only game here, so there is no symmetry at all. This is definitely a polar molecule, and the bond is polar. The most polar bond is the biggest delta chi, and that's going to be the carbon-fluorine bond, and you'd have to have the tables of electronegativity to do this. However, CF4 is a non-polar molecule because everything around it is the same. It's like if there were 4 Schwarzeneggers and they were pulling me, they'd all pull equally and stuff in a tetrahedral environment. PCl3 and CO are not symmetric, so they have a difference in how things are pulled, polar molecules. So realize there's polar molecules and you can have polar, non-polar bonds. Okay, so that's it for problem set number 4. I really appreciate you hanging out here, and I hope this has been a useful experience. If you have any questions on anything, definitely reach out to me and the LSC/Avid Center people. All of us are here to help. I have lots of resources in case you need some assistance. The study guides, the concept guides, which are in the companion and online, as well as the online-only chapter guides can all help you. And don't forget that geometry and polarity guide. A lot of these names might be new to you, but you can quickly look up these names and the bond angles, stuff like that, and figure out what's going on. Okay, thanks again for hanging out with me. I really appreciate it. I hope this has been helpful, and have a wonderful day.